How's it going, guys? Today in this video, we're going to be going over Module 9.1, Day 1. This is what the front of the packet will look like in the year that I'm recording it. This warm-up, we're going to skip the first two problems. They're pretty straightforward. You're just graphing some lines. You should know how to do that by now. And we're going to start the second half of the warm-up, and this is where we're going to talk about direct variations. And just a little reminder of what it is. So here we're told an area of a rectangle with length L and width W is given by the formula area equals length times W. And if we hold the width constant and change the length, the area will change. So basically what that's saying is that if I have a square that always has a width of 2, if I change the length, let's say I have a length of 2, then I upped it to a length of 3, the area is going to change, right? The width stays, like in the next sentence, it says it's kept at 2 inches. If the width stays at 2 inches and I change the length, the area is still going to change. So we're going to graph that relationship between the length and area of a rectangle, and we're going to figure out what the equation is going to be. So here, if I have the equation area equals length times width, where the width will always equal 2. If my length is 0, I have 0 times 2, which will be 0. If my length is 1, I have 1 times 2, which is 2. If my length is 2, I have 2 times 2, which is 4, because the width will always stay 2. So I'm multiplying whatever the length is with my width, and that gives me my area, my y value in this graph. And what I see is happening is that I really just have a regular line with a slope of 2. So this is essentially what my graph is going to look like. So this is what A equals 2 times L is going to look like. This is what this graph is going to look like. It's the area equals the width of 2 times my length. And that looks very similar to y equals 2x, because it is the exact same graph. Y equals 2. It's just a regular straight line with a slope of 2. That's exactly what it is, and that's what a direct variation is going to be. So in general, a direct variation equation is going to be written in the form y equals ax, where a, that's going to be your constant term, or the term that never changes. So in this example right here, that's what we'll call our 2, our width. It never changed, it stayed at 2. So the graph of direct variation always passes through the origin. And that's because we look at this example we just went through. If my length was 0, my area is going to be 0. So, or if I look at y equals a times x, if my x is 0, my y has to be 0 as well. So what we say is that we say a varies directly with L. 2 is the constant of variations. And just like the name says, it's the term that stays constant through all the variations that we have. Right? So in this case, the width is 2. It stayed consistently 2, no matter what variation of the length and area that we have. So now we're going to talk about inverse variations. That's the big thing of the day today. Look at what an inverse variation is. So here we're going to take that same example, the area equals length times width, but now we're going to say the area will always be 24. Whoops. So we're going to say that the area is always going to be 24, and that's what we're going to graph. So if the area always equals 24, and area equals length times width, and my length is 1, that means my width has to be 24. Because 1 times 24 gives me 24, and that's what I want. So my length is 1. On this table right here, we're going to be going up by 2s. It's the only way this will work. 8, 10, 12, 14, 16, 18, 20, 22, and 24. We're going to be going up by 2s. So my length is 1. My width is going to be 24. My length is 2. My width would be 12. Since 2 times 12 is also 24. So 2, we have 12. My length is 3. I'll have a width of 8. Same thing. 3 times 8 is 24. So 3, 8. And now if my length is 4, my width would be 6. Right? 4 times 6 is 24. So my length is 4, my width is 6. So I go to 4, I have 6. After 4, I can say my length is 6, and my length is 6. I have a width of 4. So right about here. And now my length is 8. I'll have a width of 3. So right about right here on the graph, my length is 12. I have a width of 2. So 12, 2. That's the end of my graph. And my length, when it's 24, I have a width of 1. I don't have it here. I can't graph it. But the important thing here is that we're seeing the general shape of what an inverse function looks like. My graph isn't the prettiest. Sorry about that. All right, good enough. But that's what we're going to see. And that's what an inverse graph looks like. It looks more or less something like this. An inverse relationship is a relationship between two variables, x and y, that can be written as y equals a over x. So if I look at this problem right here, where I said area equals 24, I have length times width. So I have area equals length times width. Or I can rewrite this as, I can divide by w on both sides and say that length equals area all over the width. Write that a little nicer. Length equals area all over the width, right? Where the area is 24, so I can rewrite this again as length equals 24 all over the width, right? That's what this graph is. It's length equals 24 all over my width. And that's what a inverse variation is. And we say that y varies inversely with or slash past x, and a is called the constant of variations as well. Constant of variations. Sometimes it is helpful to rewrite the equation as y times x equals, and you'll see why this can be very helpful in 9.2 day 2, where we actually use that form much more often. So this is what an inverse variation is, and a couple of things to pay attention to when it comes to inverse variations and also direct variations is that with inverse variations, as one variable is going up, so in this case when the length is going up, the other variable is going down. As length increased from 1 to 2 to 3, 4, 6, 8, 12, and 24, the width was going down. It started at 24, then went down to 12, 8, 6, 4, 3, 2, and 1. And that's what's going to happen with inverse variation. As one variable increases, the other variable will always decrease. That's what makes it an inverse variation. One goes up, the other goes down, or one goes down, the other goes up, same thing. And if we go back to the previous slide, with direct variations, it's going to be different. With direct variations, as one variable increases, the other one's going to increase as well. Right? If I see here with area and length, as the length increased, the area was increasing as well. And that's what makes a direct relationship a direct relationship. As one variable increases, the other increases as well, or if one decreases, the other decreases as well. They go the same way. All right, so now we're actually going to use this, what we just learned, to actually solve some problems. So here, we're going to write an equation relating to variables and use it to answer the questions. So the time t and days that it takes a theater crew to set up a stage for a musical varies inversely. So that's the key word of this problem right here. We're told it varies inversely as the number of workers W. So right away, I have my two variables. I have t and w. I know t and w are my two variables, and they vary inversely. So I can write my equation with just that one sentence. I can say that I know my general equation is t equals a over w. That's my general equation. That's my equation with all my variables. Remember that a term is my constant term that I'm going to solve for. The next sentence, it tells me if 30 workers can set up the stage in 4 days. That part right there, that's telling me if W is 30, T will be 4. All right, so I already have a situation right there. So I can plug that in. Before I even finish the sentence, I can plug this equation, these variables, or this scenario really, into my equation. I can solve for it. When T is T is 4, W equals 30. So I can plug in t equals 4 and w equals 30 into that t equals a over w that we have in 1. I can plug it in to get 2, and when I solve for a, I get 120, and that's what happened. Now if I go back to the sentence, to this problem, and I read the rest of it, it's telling me how many days would it take if only 24 workers are available. So now it's asking me if W is 24, what's T going to equal? If W is 24, what's T going to equal? And now that I have my A value, I can plug that back into my equation. And I know for this problem, my equation is always T equals 120 over W. So now I can plug in any W or T that I want, and I can always find the answer for the other variable. So in this case, I want to know what T is going to be when W is 24. So all I do is take that W, that 24, I plug it in, and solve for T. So T is going to be 5 days. So 120 divided by 24 will give me 5. So that's pretty much it. You write your equation with all the variables. After that, you plug in the scenario that they give you. In this case, it was W equals 30, T equals 4. Plug that in. Solve for your A term, because your A term will stay the same no matter what your T or your W are. You plug in your A back in, plug in whatever you're trying to solve for, and you have your answer. So let's do one more example. Let's go over number 2. Here, we're told the time T in hours that it takes a group of volunteers to clean up a city park varies inversely. There's that key word again, varies inversely, as the number of volunteers V. So since I know it's an inverse variation, because it tells me they vary inversely, and I know my two variables are T and V, I know my general equation is T equals A over B. I still need to solve for A. I need to solve my constant of variation, or my constant term in this problem. And I do that when they give me a scenario. And that next sentence, it tells me if 10 volunteers could clean up the park in 6 hours, how many volunteers would be needed to clean up the park in 4 hours? So that sentence right there tells me when, it's right to the side right here, it tells me if B is 10, then T is going to be 6. So I can plug that in. I can plug in 6 for T and 10 for V. And when I do, I get that A equals 60. Right? So now I know my A term, I can plug that in to get that T equals 60 over V. So what I want to solve for ultimately in this problem is what my V would be. So what is my V going to be? How many volunteers do I need if I want to clean up the park in 4 hours? Well, what's my V going to be when T is 4? So I plug in 4 for T, and then I'm just going to solve for V. Multiply by V on both sides. Since the V's on the right, these will cancel out. And I'm left with 4V equals 60, or V equals 15. So that's my V term. That's what I get. And that's number 2. So go ahead and try number 3 on your own, number 3 and number 4 on your own. And then I'll come and I'll show you the answers under there. So pause the video and come back and check your answers once you solve those out. All right, so for number 3, this is what you should have got. Ultimately, you should have got T equals 3 over 5, or 3/5 an hour, which equals 36 minutes. Right, for number 5, you should have got T equals 3/5, but 3/5 of an hour, you multiply that by 60 to figure out that's going to need 36 minutes. And then for number 4, this is what you should have got. So V and P vary inversely. So V equals A over P. 2 will be A equals A over 3, since that's our scenario. Plug everything in, figure out your constant, which was 24. Plug in what you're solving for, and you end up getting that P equals 4. And the last thing I want to end this video on is that when it comes to strictly solving what the equation is, it actually does not matter where you put your variables. Because here I have V equals A over P. I can rewrite this. I can multiply by P on both sides. And when I do, I get the left side, I get P times V equals, these cancel, equals A. And then I can divide by V on both sides. And when I do, these V's cancel out, and I'm left with P equals A all over V. So that tells me that this P equals A over V is the same thing as V equals A over V. I was able to solve for either one. So I'm just trying to show that it actually does not matter where you put your variables. All that matters is that you put the constant over one of the variables. The A has to be on top of the variable. It cannot be underneath the variable, or the equation's not going to work. All right. So anyway, guys, that's the video. I think that's the last slide. It is. So hopefully this video was helpful, guys. If you still have any questions, just rewatch the video, see how I did the problems, but hopefully this was helpful.